Imagine for a second that the numbers your computer juggles aren't always what they seem,
Hmm.
that going faster can sometimes lead to total breakdown, and that even the simplest yes or no can trigger, well, a cascade of intricate
Right.
steps. This isn't some futuristic thriller, it's happening right now inside your devices.
Yeah, exact.
Today, we're plunging into the surprisingly quirky reality of how your computer really works.
Exactly. We're about to explore the fundamental machinery that, underpins everything digital.
Okay.
Think of it as getting the cheat sheet to understanding binary, those seemingly simple instructions that control your programs, and the actual physical architecture that breathes life into them.
Great.
The material you shared that dive into intermediate computer science, it's the perfect launchpad for this,
Okay, so our mission today, should we choose to accept it,
which we have.
and we have, is to dissect this material and pull out the genuinely mind-bending and crucial bits. We want to move beyond the surface level and give you a real feel for the magic and occasional madness happening inside your tech. We'll tackle how everything boils down to binary, how your code's logic unfolds, and the hardware that makes it all dance.
That's it.
Let's kick things off with the most fundamental concept. How computers even represent information using just zeros and ones. It feels almost too simple to be true.
It does, but that simplicity is deceptive, in its power. At its heart, a computer understands nothing but on or off,
Yeah.
represented as 1 or 0.
Just that.
Just that. But what's truly fascinating is how these basic units can be combined and interpreted in countless ways.
Oh, so?
Well, that sequence of bits could be a number, a letter, maybe a pixel and an image, or even a command telling the processor what to do next.
Ah, okay.
The meaning isn't inherent in the bits themselves. It's all in how the software, the program, chooses to interpret them. It's like having an alphabet with only 2 letters that can somehow create, well, every book ever written.
And when we start writing code, we're dealing with these bits in organized chunks called data types, right? Like integers, characters, floating point numbers.
Exactly. Int, char, float, double.
The source mentions something interesting, though, that the size of these types isn't set in stone across all computers. Why is that?
That's a fantastic point, and it highlights a key challenge from the early days of computing.
Yeah.
Portability.
Right.
Different processor architectures just evolve with varying ways of handling data. So while standards like C specify minimum sizes,
Minimums, yeah.
the actual number of bytes allocated for, say, an int on one machine could be different on another. 4 bytes here, maybe 8 bytes there.
Which must have been a headache.
Oh, a major headache when trying to run the same software on different systems. That's where the size of operator in C comes in handy.
Ah, size off.
It lets you peek under the hood and see exactly how much memory a particular data type occupies on the specific hardware you're using right then.
So it adapts.
It's a reminder that the abstract world of software ultimately sits on a very concrete foundation of hardware.
Now, when we do math with these binary numbers, it's not that different from decimal, is it? Addition, subtraction.
The basics are similar, yeah. But the source also talks about bitwise operations.
Right. AND or not. Shifting. What are those all about, and when would you even use them?
You're right, basic arithmetic works similarly, but bitwise operations are where things get really down to the metal. Instead of treating a sequence of bits as a single number, they operate on each individual bit.
One by one.
Exactly. ND or R and not let you perform logical operations at the bit level. For example, a bitwise AND can be used to check if a specific bit in a number is set to 1.
Like a mask.
Precisely, like using a mask. Think of it like flipping individual switches rather than dealing with the whole circuit at once.
Then shifting.
Bit shifting operations move all the bits in a number to the left or right. A left shift effectively multiplies by powers of 2.
Okay. Faster multiplication.
Sometimes, yeah. And a right shift divides. Interestingly, there are 2 types of right shift. Logical, which always fills the vacated bits with zeros. That's common for unsigned numbers. And then there's arithmetic right shift,
Arithmetic.
which preserves the sign of a signed number by copying the leftmost bit, the signed bit.
Ah, clever. So why use them?
You might use these for low-level optimizations, sometimes for manipulating hardware registers directly or dealing with data in network protocols, really specific stuff usually.
That makes sense. Now, one concept that sounds like a recipe for disaster is arithmetic overflow.
Oh, yeah.
The odometer analogy really painted a picture. What's the big deal with this in the computer world? Is it just wrapping around?
The odometer analogy is indeed great for visualizing that wraparound effect in unsigned integers. You hit the max, you go back to 0.
Simple enough.
However, with signed integers, the consequences can be more insidious, more subtle.
How so?
Because of how negative numbers are represented using something called 2's complement, overflowing a positive signed integer can suddenly flip it into a large negative number,
Whoa, okay.
which leads to bizarre and really hard to debug errors. The Gangnam-style YouTube view counter incident is a perfect real-world example.
I remember hearing about that.
Yeah, they use a 32-bit signed integer, which has a maximum value of around 2.1 billion
Which seemed like enough, I guess.
at the time. But the video's massive popularity meant it was about to exceed this limit, potentially breaking the counter, maybe rolling over to a negative number.
So they had to fix it.
They were forced to upgrade to a 64-bit integer, which has a much larger maximum. It just highlights how these low-level storage choices can have very visible consequences, even at a massive scale.
Okay, so we've got our bits and bytes, and sometimes they can overflow in unexpected ways. Now, the source discusses how multi-byte numbers are arranged in memory, this idea of different layouts. What's the practical upshot of this?
Right, so when you have a number that takes up multiple bytes, like a 32-bit integer, which is 4 bytes, the order in which those bytes are stored in memory can vary between different computer architectures. Different CPU families might do it differently.
Okay, how?
Imagine the number, say, 0 by 1, 2, 3, 4, 5, 6, 7, 8 in hexadecimal. One system, maybe a big endian one, might store it in memory byte by byte as 12, then 34, then 56, then 78.
Makes sense. Most significant first.
Exactly. But another system, a little endian one, might store it as 78, then 56, then 34, then 12. Least significant byte first.
Backwards. Why?
There are historical reasons and minor performance trade-offs, but the key thing is that they are different. The source doesn't use the names big endian or little endian, but that's the concept.
And why does it matter to us?
This difference becomes critical when you're transferring binary data between systems with different endianness.
Like over a network.
Exactly. Or reading a file written by a program on a different machine architecture. If you're not aware of this byte order difference, you could end up interpreting the data completely incorrectly. Scrambled numbers.
Got it. Okay. And then we dive into the world of representing real numbers things with decimal points in binary. That sounds inherently tricky.
It is a bit tricky, yeah.
The source mentions fixed point and floating point. What's the core difference and why the two approaches?
Representing real numbers in binary is definitely a balancing act. Fixed point representation is conceptually simpler.
How simple?
You basically allocate a fixed number of bits for the integer part and a fixed number for the fractional part before you even start.
Okay, like agreeing you'll always have two decimal places.
Exactly like that. It's easy to understand, but it can really limit the range of numbers you can represent.
Yeah.
You can't represent very tiny numbers or very huge numbers easily.
Right, and floating point.
Floating point representation, on the other hand, is more flexible. Much more flexible. It's akin to scientific notation.
Like 1.23 times 10 to the power of 5.
Precisely. You have a significant, which is like the 1.23 part.
And the main digits?
Right. Then an exponent, like the 5, which determines the magnitude or where the binary point effectively floats.
Hence, floating point.
Exactly. And usually a signed bit for positive or negative. The widely used standard is IEEE 754, which defines exactly how these parts are stored in binary.
And the advantage.
This allows you to represent a much wider range of numbers, from very tiny fractions to incredibly large values, using the same number of bits.
But that's a catch.
There's always a catch. The trade-off is precision. Because you have a limited number of bits for both the significand and the exponent, most real numbers cannot be represented exactly.
Can't.
No. Think about 0.1 in decimal. It's a repeating fraction in binary. It goes on forever. You have to cut it off somewhere.
So you have rounding errors.
Tiny rounding errors creep into calculations. It's something many programmers don't fully appreciate, that seemingly precise calculations involving decimals on a computer are often just very, very good approximations. Not exact.
That's a really important point about the inherent imprecision. Okay, let's switch gears a bit and talk about how the code we write actually gets executed. We use if statements and for loops all the time. How does that high-level logic translate into the nitty-gritty of machine instructions?
Yeah, this is where the abstraction layers start to peel away in a really fascinating way. When you write an if statement or a loop in a language like C,
Or Java or Python.
well, C is a good example here because it's closer to the hardware. The compiler translates these high-level constructs into lower-level instructions that the processor can actually understand.
Okay.
And at its heart, this often involves the concept of jumps.
Jumps, like go to.
Essentially, yes. Think of it like having a numbered list of instructions, and instead of always going to the next number, certain instructions tell the processor to jump to a different line number based on some condition.
Ah, okay.
The source shows examples of C code and its potential translation into assembly language for different processor families, like the old IA32 or the newer ARM-V8A used in phones.
And you see the jumps there.
You do. You'll see comparison instructions, seem similar, that evaluate a condition, maybe checking if two numbers are equal.
Right.
And these set internal flags in the CPU. Then, conditional jump instructions, JMP, JL for jump is less or equal, B in ARM, look at those flags and direct the flow of execution to a different part of the code if the condition is met.
So if by 5 becomes something like compare X and 5, then jump if less than to this address.
Exactly. It's a more primitive way of controlling program flow than our familiar Eiffel structure, but it's what the hardware directly understands.
So the program counter, which you mentioned earlier, is constantly being updated to point to the next instruction.
Yep.
These jump instructions directly manipulate that counter to change the order of execution.
Precisely. The program counter holds the memory address of the instruction that will be executed next. Normally, it just increments.
One after the other.
Right. But when a jump instruction is encountered and its condition is met, it updates the program counter to a new, potentially non-sequential address.
Got it.
That effectively skips over or repeats sections of code. This is the fundamental mechanism by which computers implement all conditional logic and loops.
And C's for loop?
The source also highlights that C's for loops are quite flexible. They have that initialization part, a continuation condition check, and an update step.
Right, the 3 parts in the parentheses.
Yeah. That makes them more general than, say, Python's for loops, which are primarily designed just for iterating over sequences or collections. C's for is more fundamental in a way.
Moving on to functions, when we call a function in our code, there's a whole behind-the-scenes process involving something called the call stack. What's the crucial thing to understand about how functions work at this lower level?
The call stack.
Yeah.
It's fundamental. Function calls involve carefully managing the flow of execution and the data associated with each function.
Okay.
When you call a function, the system needs to remember where to return to after the function finishes its job.
Like leaving a bookmark.
Exactly like leaving a bookmark. This return address, along with space for any local variable the function might need, is typically allocated on the call stack.
So what is the stack?
Think of the stack like a pile of plates. When you call a function, you put a new plate on top with all the necessary info, the return address, maybe parameters, space for locals.
LIFO, last in, first out?
Precisely. Parameters are passed to functions, often using dedicated registers in the processor for speed.
Like little temporary holding spots in the CPU.
Right, like X0 by 7 in ARM-V8A, very fast. Or sometimes parameters are also placed on the stack if there are too many for registers.
And when the function is done?
When the function completes its task, the return value is usually placed in a specific register, like %XX in older by 86, or X0 in ARM-V8A.
A designated spot.
Yes. And then the plate is removed from the stack, popping off the local variables and revealing the return address underneath, so execution can resume where it left off.
And the previous state is restored.
Exactly. The source provides concrete examples, showing assembly code for simple C functions, illustrating exactly how parameters are passed and return values handled. It demystifies it quite a bit.
What about recursion? When a function calls itself?
What's fascinating is that even recursion relies on this same stack mechanism. Each recursive call just adds another layer, another plate to the stack.
So each call gets its own set of local variables.
Exactly. If you don't have a proper base case, a stopping condition, in a recursive function, you can end up with a stack overflow, which is like your pile of plates getting too high and just toppling over.
Right.
The program usually crashes.
Right, run out of stack space. So all this intricate software behavior, the jumps, the stack, it ultimately rests on the foundation of the computer's architecture itself.
Absolutely.
The source provides a good overview of these fundamentals. What are the key components we should have in mind?
Okay, at its core, a computer system is a team effort. You've got the hardware, the physical stuff.
CPU, RAM.
Right, the central processing unit, CPU, random access memory, RAM, input ports, disks. And then you have the system software, like the operating system, that manages all these resources.
And the CPU is the brain.
The CPU is the workhorse.
Yeah.
Responsible for fetching instructions from memory, decoding them, executing them, performing calculations.
And RAM?
RAM is the volatile memory, the temporary workspace where currently running programs and their data reside. Volatile means it forgets everything when the power goes off.
Okay. And the CPU has its own language.
In a sense, yes. Crucially, the CPU operates based on its instruction set architecture, or IS.
Yeah.
That's the vocabulary of commands, the specific binary instructions it understands. Different processor families have different ISAs by 8664, which most desktops and laptops use. ARM, which is in almost all phones and tablets.
Got it.
The source briefly touches on the history, too, from early human computers calculating tables,
People doing math.
yeah, to electronic marvels like Colossus and ENIAC during World War II, which paved the way for the von Neumann architecture.
Von Neumann. Still relevant today.
Absolutely. It's still the basis of most modern computers. Its key idea was using a single address space, a single chunk of memory, for both instructions and data.
Unlike earlier machines.
Some earlier ones had separate memory for instructions and data. Von Neumann simplified things. The CPU then cycles through fetching an instruction from memory, decoding what it means, and executing it.
The fetch, decode, execute cycle.
That's the one. Within the CPU, you have the control unit managing this cycle and the processing unit doing the actual work.
Which contains
The arithmetic logic unit, the ALU, which does math and logic operations, and registers.
registers again.
Yep, those small, very fast memory locations right inside the CPU used for holding temporary results or frequently accessed values. Much faster than RAM.
And the program counter keeps track of where we are.
Right, the PC holds the memory address of the next instruction to be fetched executed. Jumps modify this counter.
And modern CPUs often have multiple cores.
Yeah, multi-core processors. Essentially multiple CPUs on a single chip, allowing the system to perform multiple tasks or parts of a single task truly in parallel.
Now, with all this data moving around between the CPU and memory, speed becomes a major bottleneck, right? CPUs are way faster than RAM.
Huge bottleneck. That's where the memory hierarchy and caching come into play.
Okay. Trying to bridge the speed gap.
Exactly. There's a fundamental trade-off. Faster memory is generally smaller and much more expensive per byte. Slower memory is cheaper and larger.
So you use layers.
You use layers, a memory hierarchy. At the top, you have the super fast CPU registers, then small fast cache memories, level 1, level 2, maybe level 3 cache, then larger but slower main memory, RAM, and finally slowest but largest storage, like SSDs or hard drives.
And caching is key here.
Caching is crucial. It leverages a principle called locality.
Locality.
Yeah, which has two main flavors. Temporal locality. If you access a piece of data, you're likely to access it again soon.
Makes sense.
And spatial locality. If you access a piece of data, you're likely to access data located nearby in memory soon after.
Like reading elements in an array sequentially.
Exactly like that. Caches exploit this.
So the CPU first checks the cache, the fastest memory closest to it, for the data it needs.
Right. If the data is there, that's called a cache hit.
Fast path.
Very fast.
Yeah.
Access is quick. But if the data is not in the cache, a cache miss.
Slow path.
It has to go all the way out to the next level, maybe L2 cache or L3, or even all the way to the slower main RAM to fetch it, which takes much, much longer.
And that difference matters.
The performance difference between a cache hit and a cache miss can be enormous, like hundreds of clock cycles.
Wow.
Caches can be organized in different ways too, like direct mapped or set associative, which affect how memory addresses map to cache locations, influencing hit rates.
And this affects programmers.
Oh, definitely.
Yeah.
What's really interesting from a programmer's perspective is that even the way you structure your code and access data in memory can have a big impact on cache performance.
Like the array example.
Exactly. When working with multidimensional arrays in C, which stores them row by row, accessing elements in that same row major order is usually much faster.
Because of spatial locality?
Precisely. You access one element, the cache likely pulls in the next few elements in that row too. Accessing elements column by column jumps around memory more, potentially causing more cache misses.
A subtle but potentially big optimization.
It really can be.
This makes me think about the role of compilers. They take our nice high-level C code and turn it into these low-level, potentially cache-aware machine instructions. The source touches on compiler optimizations. What kind of tricks do compilers have up their sleeves to make our programs run faster?
Modern optimizing compilers are incredibly clever pieces of software themselves. They analyze your code deeply to identify areas where they can improve performance without changing the program's fundamental behavior.
What kinds of things can they do?
Well, some common techniques include constant propagation. If you have x equals 5, y equals plus 2, the compiler might just calculate y equals 7 directly.
Computes it at compile time.
Yeah. Dead code elimination, removing code that can provably never be executed.
Makes sense.
Loop invariant code motion, you have a calculation inside a loop that doesn't depend on the loop variable The compiler might move it outside the loop so it only runs once.
Instead of thousands of times.
Exactly. Saves a lot of redundant computation. There are many, many other optimizations too.
But there's a trade-off.
There can be. Sometimes really aggressive optimization can make the resulting assembly code much harder to understand and debug if you ever need to look at it. It might not map cleanly back to your original source lines.
Right. Debugging optimized code can be tricky.
It can.
And speaking of debugging, when things do go wrong, we rely on tools. The source mentions GDB and Valgrind. What makes these so useful?
Oh, they're lifesavers. Debuggers like GDB, the GNU debugger, are essential for stepping through your program's execution line by line or instruction by instruction.
Watching it run slowly.
Basically, yeah. You can inspect the values of variables at any point, see how the program's state changes, and understand the flow of control. You can set breakpoints to pause the program at specific locations.
To examine things.
Right. And Valgrind is particularly powerful for memory-related errors, which are notoriously hard to find in languages like C.
What kind of errors?
Things like accessing memory you haven't allocated, reading uninitialized memory, writing past the end of an array buffer. Valgrind runs your program in a special environment and flags these dangerous operations.
Super useful for C++ app.
Absolutely essential sometimes. These tools let you peer into the inner workings of your program at a very detailed level, helping you pinpoint bugs that might be completely invisible just reading the source code.
And sometimes you might even look at the assembly.
Yeah, sometimes, especially if you don't have the original source code or the bug is really low level, engineers might need to reverse engineer or just examine the assembly code directly to understand exactly what the program is doing.
Finally, the source touches on a critical security issue. Buffer overflow. It sounds like a vulnerability that can have serious consequences.
It absolutely can, and historically it has been the source of countless security exploits.
Oh, what is it exactly?
A buffer overflow occurs when a program tries to write more data into a buffer, which is just a region of memory allocated to hold a certain amount of data, like an array for user input.
Okay.
Tries to write more data than that buffer was designed to hold.
Right.
The excess data spills out and overwrites adjacent memory locations.
What's in those adjacent locations?
Could be anything. Other variables, crucial control information like the function's return address stored on the stack.
Ah, the return address.
Exactly.
Yeah.
If an attacker can carefully craft input that overflows a buffer and overwrites the return address, they could potentially redirect the program's execution to malicious code that they injected as part of the overflowing data.
Taking control of the program.
Taking control. The source mentions historical examples, like the Morris worm back in '88, one of the first major internet worms, which exploited buffer overflows. It was a huge wake-up call.
So how do we prevent this?
Prevention involves a combination of things. Crucially, using safe programming practices in languages like C, for instance, using functions like strainaspy or stensprintf, which limit the number of bytes copied or written, instead of unsafe functions like strainascopy or gets, which don't check bounds.
Always check your bounds.
Always perform bounds checking. Don't trust input sizes. Modern operating systems also help with defenses like marking the stack and heap memory regions as non-executable, making it harder for injected code to run even if an overflow occurs. Address space layout randomization, ASLR, also makes it harder for attackers to predict where things are in memory. But careful coding is the first line of defense.
Wow, okay. From the fundamental binary digits all the way up to complex security vulnerabilities like buffer overflows. This deep dive has truly illuminated the many layers of abstraction that underpin our digital world.
It really has.
It's astonishing to see how these seemingly theoretical concepts, binary representation, endianness, caching, stack frames, have such tangible and sometimes critical real-world implications.
It is. And a deeper understanding of these fundamentals, it not only helps in appreciating the sheer complexity of modern computing, but it also empowers you, as a developer or even just a user, to understand why things work the way they do and potentially write more efficient, reliable, and secure software.
On that thought, here's something to consider. How might the seemingly simple choice of using a particular data type, maybe just deciding between a signed int versus an unsigned int in your code, how might that have unexpected consequences down at the low level, especially when you think about potential overflows or bitwise operations?
That's a great point.
What other seemingly minor programming decisions might have surprising ripples all the way down to the hardware, affecting performance or correctness in ways you didn't initially expect?
That's a fantastic question to ponder. The landscape of computer systems is just vast and constantly evolving. The topics we've explored today are really just scratching the surface.
Just the beginning.
Absolutely. We really encourage you to continue your own deep dive into the areas that sparked your curiosity. Maybe that's exploring the assembly language for your own computer, or digging into the fascinating world of compiler optimizations, or understanding the ongoing challenges and innovations in computer architecture.
Yeah.
The journey into the inner workings of computing is a truly endless and I think a really rewarding one.